In this video, we're going to learn another method of proof called proof by contradiction. So here's the idea. We start by stating suppose not or suppose to the contrary and state the negation of the quantified statement. So we're given a statement, we say suppose our statement isn't true. Okay. So recall we're going to have universal statements with conditionals. So recall the form of the negation of such a statement. It's easily read in this lovely symbolism. Or you can just see that what we're going to do is change the for all x to there exists an x. Okay. And instead of writing if p then q, we're going to change it to p and not q. Okay, so that's how you negate a universal. Then we're going to make arguments that follow from the supposition until you reach a contradiction. So basically what we're going to do is we're going to say, suppose it wasn't the case that what we're trying to prove is true. Well, then this would be true, and this would be true, and this would be true, and that's going to make some contradiction that tells us it's impossible that the negation is true. Okay, so let's get started. So provide a proof by contradiction of the statement below. So this is the same proof we did in the last problem, but we're going to prove it via a different method. So prove that for any integer x, if x squared is even, then x is even. Okay. So first, let's write this negation out so we know how we're going to start our proof. So here's the negation. Instead of for any integer x, we say suppose there exists an integer x such that, so you put such that after there exists. And now we say x squared is even, so this is true, but this is false, and x is even is false, or x is odd. So this is our negation. So we're going to start our proof by saying, suppose to the contrary that there exists an integer x such that x squared is even and x is odd. And we're going to show that this leads to some sort of contradiction. So we write proof, suppose to the contrary that there exists an integer x such that x squared is even and x is odd. So now we use the definitions just like we've been doing. Since x squared is even, that means there exists an integer k sub 1 such that x squared equals 2 times k sub 1. And since x is odd, which we assumed, there exists an integer k sub 2 such that x equals 2 times k sub 2 plus 1. Okay. Now in the other problems we had some conclusion we wanted to reach. We assumed one and then we tried to show the other is true. Here we're assuming one and the negation of the other under an exists. So we want to somehow use these and rewrite them so we get something that's contradictory. Okay. So our options are we have x squared equals 2 times k sub 1. We could write that as just x, but that's difficult because how would we find the square root of this? Or we can take this expression and square it and FOIL it out like we did in the last problem. So let's do that and see what happens. So now if we square both sides of the equation for x, we have x squared equals, and this should look familiar. I literally pasted it from the last problem we did. I'm going to update these. They should be 2's, not 1's. So just as we saw in the last problem, when we FOIL this out and we factor out a 2 and rewrite this expression, okay, we see that this is going to be 2 times an integer. We'll justify this as an integer in a second, plus 1. So this is going to mean x squared is odd. Okay, but we stated in the beginning that x squared is even. So that's our contradiction. So let's write that up. So now we state, like we did in the last proof, since the integers are closed under multiplication and addition and k sub 2 is an integer, this expression is also an integer. Now we redefine k to equal that expression, and then we can write x squared equals 2 times k plus 1 where k is an integer. Okay. But by definition, this means that x squared is odd, but x squared is even by assumption, which is way up here, which is a contradiction. Okay, and after we get contradiction, sometimes we draw 2 arrows going into each other, meaning they contradict each other. So, therefore, for any integer x, we state the original statement we were trying to prove. If x squared is even, then x is even, QED, and we're done.